In the name of God. Hello, dear students. Welcome back to Ferho's website. My name is Masoud. I'm a physics teacher. We are here to explain physics curriculum, grade 12. In previous lessons, we finished chapter 1 and we answered and solved some questions and problems that have to do with the chapter. And right now, this is the last, let's say, part of the chapter 1, which is standardized test prep, page 29, right? Let's move on to the question number 1, which is a question of, and some questions, let's say, the first questions are multiple choices, and let's discuss them together with one another. Number 1, an object moves in a circle at a constant speed. You see, it says constant speed. What does it mean, constant speed? There's no acceleration. Which of the following is not true? Which of the following is wrong, right, for the object? An object moves in a circle with constant speed, with constant rate, so it doesn't speed up. It's neither speed up nor slows down, right? Let's say part A, it says its centripetal acceleration points toward the center. Of course, it's true. Centripetal acceleration, AC, points toward the center of the circle. It's true. Its tangential speed is constant. Tangential speed is constant, yeah, because it mentions it in a question, says at constant speed. So tangential speed is constant, no problem. We believe it. See, its velocity is constant. So we don't buy this option. This option is not true. Its velocity is constant. Velocity can't be constant because velocity is a vector quantity, and especially about the object moving in a circle, it can't be constant because any object moving in a circle changes its direction perpetually. That's why it's not true. So till now, C is true. C, I mean the answer. The answer is C till now because it says which option is not true. C is not true. So D, centripetal forces act on the object. Of course, for any centripetal, for any, let's say, for any object moving in a circle, there must be a centripetal force. So you cannot eliminate centripetal force from the phenomenon. That's why the answer is C. This one is wrong. Question number 2, use the passage below to answer question 2 to 3. So there's a passage. This passage is dedicated for question number 2 and 3. Let me read it for you. So it says, let me read the passage for you. A car traveling at 15 meters per second, right? This is the, let's say, velocity or speed of a car on a flat surface. It's an ordinary surface. It's not a banked curve or sharp turn, right? Turns in a circle with a radius of 25 meters. So the radius is 25. And velocity or centripetal, or excuse me, tangential velocity is 15 meters per second. So this is VT, right? VT. It says A. Excuse me. So this is the, let's say, passage. The passage talks about an object, a car traveling in a circle with this velocity and on that radius with velocity of 15 meters per second on a circle with a radius of 25 meters, right? So it's a question number 2. What's the centripetal acceleration of the car? So we look for AC. AC is unknown. There are some options, A, B, C, D. So firstly, you have to solve the problem. After that, after solution, you can guess which option is true, right? AC is equal to VT squared over R. Vt 15 meter per second square divided by 25. Actually, 15 square means 225 divided by 25 becomes 9. So 9 meter per second square is the true answer. So this option is true. Question number 3. What's the most direct cause of the car centripetal acceleration? Let me tell you something. It says, what's the cause? What's the main cause of centripetal acceleration? It means what thing causes, which factor causes, let's say, centripetal acceleration. Maybe you say, teacher, we haven't been familiar with this, let's say, type of question, because in previous lessons, we look for the source of FC, not AC. So keep in mind that source of FC is as the source of AC. It doesn't matter. When the question says, what's the main cause of centripetal force, or what's the main cause of centripetal acceleration, it's the same, right? Don't be confused. It's the same. So any factor that causes centripetal force, it causes centripetal acceleration as well. So let me read the question. A rectilinear motion of the car. And actually, the car moves in a circle, right? It moves in a circle with constant speed. It says the rectilinear motion of the car, so it can't be. The rectilinear motion of the car, it can't be the source of centripetal acceleration. We don't believe it. B, the motion of the car with a constant velocity. Motion of the car with a constant velocity. Actually, I told you velocity can't be constant because the object moves in a circle, right? Firstly. Secondly, velocity can't be constant. Let's say velocity is a vector quantity. If the option says the motion of the car with a constant speed, no problem. But actually, this option, if you replace velocity with speed, it's wrong, right? Motion of the car with constant velocity or speed, it's not the source of, let's say, centripetal acceleration. So centripetal acceleration has a particular reason, right? As a particular source. Let's search for the other, let's say, factors. See, the force of friction, you see, between the tires and the road. So friction. I told you in previous lessons that the friction is in charge of centripetal force in what? In flat surfaces. In flat circular track, only friction is in charge of creating centripetal force, right? The normal force between the tires and the road. Normal force can be a source of centripetal force and acceleration, no problem, but not in a flat surface. It can be a source of, let's say, centripetal acceleration or centripetal force, especially in a sharp turn. So the only answer, let's say, true answer is C. The force of friction is the cause of centripetal acceleration. Let's move on to question number 4. Let me read the question for you. It's a problem. The problem talks about the celestial objects. Our planet, it says, question number 4, Earth, this is the mass of Earth, 5.97 times 10 to the 24 kilogram, orbits the sun. And the sun, this is the mass of sun, 1.99 times 10 to the 30 kilogram at a mean distance of 1.5 times 10 to the power 11 meters. This is the average distance between Earth and sun. 1.5 times 10 to the 11 meters. What's the gravitational force of the sun on Earth? So we look for Fg, right? And by the way, this is a question of national exam. In the question, actually, G is given. G is equal to 6.673 times 10 to the negative 11 Newton meter square by kilogram square. There are 4 options. This is the actually question of national exam. It says we have sun versus earth. We look for the gravitational force between sun and earth, and we have enough information. We have mass of each, let's say, each celestial object. We have the mean distance between, let's say, 2 bodies. That's why everything is available for finding Fg. Fg is equal to G capital M small M capital divided by R squared. Here, can I say M1, M2? No problem, as you like. Can I say M capital, M small? It doesn't matter, so no problem. Fg is equal to G capital. So G capital is constant. You have to write the number. And I recommend that, I recommend you to memorize this value. Maybe it's not given in the national exam. M small, mass of earth, M capital, mass of sun, divided by radius square. You have to square the radius. This is the distance between, radius here means the distance between the center of sun and center of earth. 1.5 times 10 to the 11 square, right? Actually, R here stands for the distance between the center of the objects, not the radius, because there are 2, let's say, individual or 2 independent objects. That's why R can't be radius. It's the mean distance between sun and earth. So anyway, you have to square the distance between sun and earth, multiply these numbers together, and divide it by, I want you to divide by the this number square to find the answer. So this is the answer. You use a calculator, and by means of calculator, you find this number, 35.2 times 10 to the 20 Newton. Let's search for this number in a multiple choice, right? In multiple choices, A, 5.29 times 10 to the 32. So it's very far from this answer. It can't be. B, 3.52 times 10 to the 22 Newton. Look here. It's very close to the number, but it's not exact number actually, right? Here we have 3.52. Over there we found 35.2. Here in the option B, we have 10 to the 22 Newton. Exponent is 22. Here exponent is 21. So I want you to, let's say, convert this one. I want to turn it into the, let's say, 10 to the power 22. Convert this one. Let's say, how many decimal points are there for the, let's say, coefficient? For the, let's say, for the number, we have 35.2. Only we have one decimal place, excuse me. Only we have one decimal place. I want you to bring the decimal point between 3 and 5. So what happens to the number? The number will be 3.52, you see? So what did I do? I added one decimal point, right? I added one decimal place. That's why I have to add the exponent, let's say, as well, because any, let's say, any changes that is taking place in a, in the, let's say, in a coefficient, any change is taking place in a coefficient should be taking place in the, should be take place in what? Should be take place in the exponent as well. So I added one decimal point. I have to add one to the exponent. So the exponent becomes 22. So the answer is 3.52 times 10 to the 22. It's the exact number of the multiple choice. About the C, actually, C can't be because the answer is very far from our answer and the exponent is negative. About the D as well, we have the negative exponent. So this answer is true, right? So I want you to practice, let's say, scientific notation, reinforce your ability in mathematics, especially because, let's say, we need to do some operations after the solution to get the, let's say, exact number among the multiple choices. All right, so this is the question of national exam. Let's move on to question, lesson number 5. Question number 5 says, which of the following is the correct interpretation of the expression AG? A sub G is equal to G small is equal to G capital mass of Earth divided by R square, means radius of Earth square. Which of the following is the correct interpretation? Actually, I proved this equation for you during my explanation, right? It talks about A sub G means G. Acceleration due to gravity depends on 3 constants. What are the constants? Let's say universal gravitational, let's say constant of universal gravitational, G capital. Mass of Earth is constant and radius of Earth. So, let's read the options to get the correct interpretation for this equation. It says A, gravitational field strength changes with an object's distance from Earth. Gravitational field changes. It talks about, let's say, gravitational field means gravitational force, let's say, right? Gravitational force. Field is in charge of pulling the objects down the Earth. Gravitational field, I can say, is a field that applies force to the object. This field is in charge of exerting force on object to fall them down toward the center of Earth. Actually, this option is true. Gravitational force strength changes with object distance from Earth, right? The closer the object is from the surface of Earth, the greater the gravitational force, and vice versa, right? Let's say the farther the object is from the surface of Earth, right, the less the gravitational field. So it's true. B, free fall acceleration changes with an object distance from Earth. Free fall acceleration changes. Is it true? Changes with an object distance from Earth. Free fall acceleration means G actually. It says changes with an object distance from Earth. G actually on the surface of Earth, right? On the surface of Earth, G is equal to 9.81 meter per second square. But at the very, let's say, distant, positions from the surface of Earth, G gradually reduces. G gradually reduces when the object goes up, right? And in some, places within the atmosphere, G becomes 8 meter per second square. That's why G changes with the position. Even, let me add one more information for you about the G. Even in the equator, right? In the equator, I told you equator sticks out at, Earth sticks out at the equator. So gravitational, I can say exertion due to gravity is equal to 9.78 in equator. So it reduces, right? It's not the same number. But at poles, especially at pole, we have 9.83 meter per second square. So by changing the position of object according to the center of Earth, right, gravitational force changes. The farther the object is from the center of Earth, the less the acceleration due to gravity is, and vice versa. Because poles are very close to the center of Earth, that's why they have the, let's say, they have the maximum amount of acceleration due to gravity, which is 9.83 meter per second squared. So B is true as well. C, free fall acceleration is independent of the falling object's mass. It's true. It doesn't depend on the mass of object based on this equation. Take a look at this equation. It says G is equal to G capital, mass of Earth divided by radius of Earth. Do you observe, let's say, mass of object or not? No. So that's why, let's say, mass of object does not affect the acceleration due to gravity, or in other words, I can say acceleration due to gravity is independent of mass of object. So D is true. All of the above interpretations are correct, right? Let's move on to question number 6. Question number 6. What do you need to calculate the orbital speed of a satellite? Right? So we want to, let's say, calculate the orbital speed of a satellite. We want to, let's say, measure the tangential velocity of the satellite, or tangential speed of a satellite. Which information is, let's say, needed for which purpose, for this purpose, right? So we look for VT. A, mass of satellite, mass of planet, radius of orbit. Mass of satellite, mass of planet, radius of orbit. B, mass of satellite, radius of planet, orbit of, area of orbit. I just underlined the information of satellite here. I'm gonna tell you a note to, let's say, to find the correct answer. C, mass of the satellite and radius of the orbit only, right? D, it says mass of planet and radius of orbit only. I want you to find the word satellite in the option D. Do you, let's say, find, let's say, do you see any, do you see word satellite here in option D? No. That's why, and this is my note. Whenever you want to find the tangential velocity of the satellite or orbital speed of a satellite, no problem, it doesn't matter actually. You want to find the velocity of a satellite. So mass of information of satellite does not matter, right? Information of mass, satellite don't matter. Don't care about the information of satellite. So whenever you observe satellite, ignore it. Don't care about it. Don't circle it. So the only option that does not involve actually satellite, only option D. Focus on the information of planet only, because mass of satellite is nothing compared to the mass of planet, because planet is an enormous object, right? It's a huge object. That's why mass of satellite is nothing. Mass of satellite is negligible for finding the velocity, even for finding the velocity of the satellite itself, right? So the only option is mass of planet and radius of orbit only, right? And I've written this note for you. Only take the information of planet. That's it, right? Take the information of planet and ignore the information of satellite. Question number 7. Which of the following choices correctly describes the orbital relationship between Earth and the Sun? So which option is true? It's about the, let's say, a relationship between Sun and Earth. This is a question of national exam. Question number 7. Let me read the option. A, the Sun orbits Earth in a perfect circle. So there are two mistakes here. Firstly, Sun does not orbit the Earth, because Sun is bigger than Earth, and larger object don't orbit the smaller object. That's the first mistake. The second mistake, it says a perfect circle. Orbits of the, let's say, planets are not perfect circle, right? So it's wrong. B, Earth orbits the Sun. Till here is true, till here. Earth orbits the sun. Yeah, Earth is smaller than sun. That's why it orbits. It orbits it, no problem. But it says in a perfect circle. So we don't buy the second part of the statement. That's why it's wrong. C. The sun orbits the Earth in an ellipse. In an ellipse. So the first part of the statement is wrong. That's why we don't care about it. Even if it talks about the correct orbits of planets, it says ellipse. But actually, sun does not orbit the Earth. It's opposite. D. Earth orbits the sun in an ellipse. Nice. Earth orbits the sun in an ellipse, in an egg shaped actually, with oval shape, with the sun at one focus. This is the law of Johannes Kepler. Johannes Kepler said this. That's why this one is true. Earth orbits the sun in an ellipse, and the sun is one of the one of the focuses of of elliptical shape. Let's move on to another question. Question number 8. It's the question of national exam as well. And question number 9 is preliminary, no problem. Question number 8, let me read the question for you. It says, which of the following statement is correct? Question of national exam. I mentioned it over there. So which one is correct? Search for the correct option. It says mass and weight both vary with location. Vary means change, right? Both vary with location means change. They change with location. Actually, only weight changes with location, not mass. Mass is constant. That's why mass is constant everywhere. It doesn't change. All right, right. So A is wrong. B, mass varies with location. It's wrong. So we don't believe it. Mass does not change at all. That's why let's move on to option C. C says weight varies with location. Till now it's true. Weight varies with location, but mass does not. Cool. It's the nice, let's say, interpretation. It's correct, right? Till now C is correct. D, neither mass nor weight varies with location, and it's wrong. That's why only C is true. Mass does not change, but let's say weight changes from location to location. Question number 9, it's the question of preliminary exam. Which astronomer discovered that the planets travel in an elliptical rather than circular orbits? Which one, let's say, said that the orbits of a planet about the sun is let's say is oval or egg-shaped or elliptical, right? Johannes Kepler. I spoiled the answer in the previous question. Johannes Kepler. B, Nicholas Copernicus, right? C, Tycho Brahe. D, Claudius Ptolemy. Actually, in our textbook, we are not familiar with Copernicus, Ptolemy, Brahe. Only we have information about the Johannes Kepler. That's why A is true. This person, this guy, this scientist corrected the mistake of Galileo, and Galileo said that the planets orbit the sun in a perfect circle, but Kepler didn't buy this idea and he corrected the mistake of Galileo. Question number 10. Are the bodies that move in a circular path in equilibrium? Why? Right? Are bodies move in a circular path is considered to be in equilibrium or not? Why? So bodies that moves in a circular track are not considered, let's say, in equilibrium. Why? Because they undergo an unbalanced force. Because they experience an unbalanced force. which is centripetal force, and accelerates the object, which accelerates the object actually. So keep in mind that any object undergoes centripetal force. It's not in equilibrium because the object picks up acceleration. Any object with acceleration is not in equilibrium. That's why acceleration, let's say, don't match with equilibrium. Equilibrium is not, let's say, they don't coincide. Acceleration and equilibrium don't coincide with one another, right? That's why whenever you hear the word acceleration, means the object is not in equilibrium, right? So that's why are the bodies that move in a circular path in equilibrium? No, because objects in circular path undergo centripetal acceleration, right? They have this centripetal acceleration due to their, let's say, their track, right? That's why, because they pick up centripetal acceleration, they are not in equilibrium. That's it. I wrote a note for you for, let's say, better understanding the subject, and I explained it for you early, right now for you. Tip: objects in equilibrium have no acceleration. I told you, acceleration don't come with equilibrium. They are opposite to one another, right? It means they are either at rest or move with constant speed. So the object in equilibrium must be either at rest or move with constant speed. That's why an object moving in a circular track is not in equilibrium. That's all for today, guys. Thank you for watching this video, and bye for now.